When a new disease hits, it feels like chaos, right? It's confusing, it's scary, but what if I told you there's a science to predicting it? Today, we're going to pull back the curtain and see exactly how scientists work to turn that chaos into clarity. So that's the big question, isn't it? How do you possibly predict the path of something you can't even see? Well, it's not a crystal ball. The answer, believe it or not, is in math, specifically the really powerful world of mathematical modeling. And that's what we're diving into. Okay, so let's start with the core problem. At the very beginning of an outbreak, public health officials are just flooded with unknowns. They need some kind of tool to see the big picture, and that's exactly where these models come into play. I like to think of a model as a kind of map. A map of a city isn't actually the city, right? It leaves out tons of details, but it shows you the important stuff, the main roads, the landmarks, so you can figure out how to get from point A to point B. Well, epidemic models do the exact same thing. They simplify the crazy complexity of a disease to show us the potential paths it could take. All right, so how do these things even work? What's kind of cool is that these super complex models all start with a really simple idea. You just sort the entire population into different buckets, or what scientists call compartments. And I mean really simple. The most basic model of all just splits everyone into two fundamental groups. That's it. This first one is called the SI model. S is for susceptible. That's basically anyone who is vulnerable to the disease. And I is for infected. The whole point of the model is just to track how people move from that S bucket over to the I bucket. Simple as that. Okay, but you can probably already spot the problem here, right? In this simple model, the number of infected people just keeps going up and up and up. It never comes back down. And we all know that's not how it works in the real world. Epidemics end. People recover. So to fix that pretty big flaw, we have to make the model more realistic. And we do that by adding, you guessed it, a third box. This is where it starts to get really useful. And that brings us to the famous SIR model. We add an R for recovered or removed. So now people can go from susceptible to infected, and this is the key, from infected to recovered. This simple change suddenly makes the model way more powerful because it actually reflects how most diseases work. And when you plot this out, you get something you've probably seen 100 times, the classic epidemic curve. Look at this. The number of susceptible people steadily drops. At the same time, the infected group shoots up, hits that peak, and then starts to fall. Why? Because those people are moving into the growing recovered group. That classic rise and fall, that's the fundamental shape of an outbreak. But here's the thing. Even a powerful model like SIR is still just a starting point. Think of it like a perfect, clean blueprint for how an epidemic should behave. But we all know the real world is, well, it's a lot messier than any blueprint. So scientists have two main ways to handle this messiness. On one hand, you have deterministic models. That's the blueprint. It's non-probabilistic and gives you one single average outcome. But on the other hand, you have stochastic models. These are built for the real world. They're probabilistic, meaning they factor in randomness and chance. And instead of one answer, they give you a whole range of possible scenarios. And the research paper we're drawing from for this explainer puts it perfectly. The deterministic approach gives you the general idea, the overall insight. But the stochastic one, that gives you the range of what could actually happen in the real, messy world. You really need both. Okay, so we've got the basic machinery down. Now let's talk about the single most famous number that comes out of all this modeling. It's one number that can tell you almost everything you need to know about how dangerous an outbreak really is. I'm talking about R0, or R0. You've definitely heard of it. It's the basic reproductive number. And all it means is this. On average, how many other people will one sick person go on to infect in a population where no one has immunity? That's it. It's the engine that drives the whole epidemic. So if R0 is bigger than 1, say it's 2, that means every sick person infects 2 more people. Those 2 then infect 4. Those 4 infect 8. You see where this is going. The epidemic is growing, and it's growing fast. Now, if R0 is exactly 1, things have stabilized. Each sick person is only infecting 1 new person. They're just replacing themselves. The number of cases isn't growing anymore, but it's not shrinking either. And finally, the goal, if R0 is less than 1, the epidemic is on its way out. It's running out of steam. Each sick person is infecting, on average, less than 1 other person. The chain of transmission is broken, and the disease will eventually fizzle out. And this is the absolute key takeaway. Every single thing we do in public health, Quarantines, wearing masks, vaccines, heck, even just washing your hands, it all has one single goal. Push that R0 number below the magic threshold of 1. That's the whole ballgame. So, compartments are not stochastic models. It's a lot of math. But why should you care? What does this actually mean for us in the real world? Here's the best analogy I've heard. Think of these models as a weather forecast, but for diseases. The weather forecast isn't always perfect, right? It might say a 30% chance of rain and you don't see a drop. But it's still our best scientific guide for what's probably coming. Same thing here. What these models do is pretty amazing. They take in just massive amounts of data, everything from lab results to how people are behaving, and they crunch it all down into a mathematical system we can understand. The output tells us, is it spreading faster? Are our interventions working? And that information is absolutely critical for the people making the tough life or death decisions. So in the end, these models don't just predict the future, they give us the information we need to change it for the better. They give us the power to prepare, to react, and to save lives. The only real question left is how we choose to use that power.